Now we're going to spend a little time talking about symmetry. So in this section of our notes, we're going to take a look at something that you actually undoubtedly know from our study of parabolas and quadratics. You know that they, for example, have a symmetry. However, we're going to take a more general view in this section. We're going to talk about the fact that a number of graphs have some form of symmetry to them. Symmetry could be useful in graphing an equation, since it really says to us that if we know what one portion of the graph looks like, then we could actually graph the remaining portion of it as well. So in this section, we're going to look at two kinds of symmetry. We're going to be looking at what we would call y-axis symmetry, and we're going to be looking at symmetry about the origin. You might ask yourself, why are we not going to talk about x-axis symmetry? Well, in order to have x-axis symmetry, we would not have a function. And we're going to be looking at function symmetry here rather than just general symmetry. It's important to note, by the way, that most graphs don't have any kind of symmetry. And it is actually possible for a graph to have more than one kind of symmetry. So first of all, let's take a look at y-axis symmetry. Y-axis symmetry really is illustrated in this graph that I now have on the screen. And what y-axis symmetry says is if xy is a point on the graph of a function that is symmetric about the y-axis, then so is the point negative xy. So if we have something that's y-axis symmetry, we're going to have these pairs of points. We'd have the point xy, and we'd have to have another point on the graph that looks like the negative of x and keep the y. And so in order to have that, every single point on the graph has to have a pair of the other form. Now, just a piece of terminology. Functions with symmetry about the y-axis are called even. So functions with symmetry about the y-axis are even. So what we can do is we can talk about this with a little bit more of a function sense. And so if I do that, I come up with this particular definition. If f at x is a function, then f is called an even function if for all x in the domain of f at x, that f evaluated at negative x equals f evaluated at x. This really says exactly what we said up above when we said if xy is on the graph, negative xy is on the graph. But from a function sense, it actually says if I computed f at x and I computed f at the negative of x, every single time I should get the same y value. So the graph of an even function, remember, is then symmetric about the y-axis. We actually use this above definition to what we might say prove a function's even. So let's take a look, and we'll take a look at an example here. So what I'd like to do is I'd like to show algebraically that f at x equals 3x to the fourth minus 5x squared plus 1 is symmetric about the y-axis, or that it's even. So what we're going to do is we're going to evaluate f at negative x. Now it's important for you to realize I'm doing it for the generic negative x. Sometimes students will say, hey, I'm going to try it for f at negative 2 or f at negative 4. That's good, but that only shows for one value. We want to do it for all values, so we're going to use f at negative x. So if I do that, I do f at negative x, and that really means substitute negative x in every place we have an x in the original function. So doing that gives me f at negative x is equal to 3 times negative x to the fourth, remember the negative will be raised to the fourth, minus 5 times negative x quantity squared plus 1. Now we know enough math, really, to know that when I raise a negative to an even power, that the negative will be kind of multiplied out and become positive. And so when I do that, I end up learning that f at negative x is 3x to the fourth minus 5x squared plus 1, which hopefully we notice is the exact function we started with. Since that's the case, we then say that f at negative x equals f at x, and when this occurs, we would then say the function is even. Now some of you might say, now wait a minute, is the function even? Is one of the ways I can tell by looking at the exponents on the x's. And that is a clue. I encourage you to be careful because I can create problems where the function is a little more complicated, and you might look and say, oh, all even exponents and it's even, and I might have actually generated something that either doesn't have any symmetry, or I might have messed with things enough that I could actually make something that's not even, that's actually what we call odd. But it is kind of a clue, and notice the x here would be to the fourth, the x here is to the second, those are both even. On the 1, and this is the part you have to be tricky, or that's a little tricky, that would actually be the same as x to the 0, 1 times x to the 0, and so you could actually say, oop, yep, that is even. That's kind of a neat little hint, but please don't use that as your only means to tell whether a function's even or odd, especially when we get into other functions like sine and cosine, and if we were to look at some of the other types of functions, some rational functions. So be really, really careful with that.